a power, an indeterminate situation that is a power. There are three. 0 raised to 0, which we knew from childhood. Infinity raised to 0, which is this case today, right now. And 1 raised to infinity, which is the third one. Once I get one of these, I have no choice but in step 1, denote the function. In step 2, apply natural log as we did, because we cannot differentiate, we cannot find the limit. We're not differentiating like this, but I'm going back, I'm connecting the topics. You knew exactly what to do because we used logarithmic differentiation to differentiate. I apply natural log to both sides. Then I apply the limit operator to whatever was given to us. In this case, it was when x approaches infinity. I do step by step everything I need to determine this limit of the natural log. When I finish that in step 4, I copy the beginning of step 3 and I copy the end of step 3. Now, because everything is continuous, so under continuity only, I'm allowed to swap the operators, make the limit touch the function and the natural log go outside. I put the limit next to the function and natural log outside. And at this point, I'm really solving a logarithmic equation. E to this power is the limit. So e to the first power is e, and that's the limit. So with the next examples, I'm not going to mention step 1, step 2, step, you know exactly what I mean, unless you want me to. And let's choose. I'm sharing my screen. Any other power? And then I'd like to continue with something else. Anyone would like to choose another power, or you're going to say, I'm fed up with those powers, enough? I think we should do it one more example, but it's up to you.
70.
70. Okay, very good. So let me copy, make sure I copied 70. Limit as x approaches infinity. And we have 2x minus 3, 2x plus 5, and the power is 2x plus 1. Okay, so now please get engaged in the sense that tell me what to do, and I'll do it. Don't tell me to jump from the Empire State Building, please. Tell me the steps.
Plug it in?
Yes. Let's start with the power.
That approaches infinity.
Awesome. Now, you could say, I don't know how to determine this because I have to differentiate because it's infinity over infinity. Okay, differentiate and tell me where this is going when x approaches infinity. Or you may remember something from calculus, from pre-calculus. Because it's an infinity and infinity, when you differentiate this, what do you get?
1.
Yes, 2 over 2 is 1. Very good. And now let's analyze which case are we looking at.
One to the power of infinity.
That's it. Another indeterminate case. We have no clue what it will come up to be. So let's go ahead. Step 1, what do I have to write? Anyone?
y equals 2x minus 3 over 2x plus 5 of 2x plus 5.
Very good. And the next step,
Natural log,
You have to do the outside, so
good.
2.
Do not forget to put 2x plus 1 in parentheses. I did not need parentheses on this previous situation. Let me go back to, because it was 1 over x. But now the power has addition or subtraction. So if you forget parentheses, the whole thing collapses.
Log natural.
Good.
inside.
Very good. Awesome. What is the next step? I named the function. I applied natural log. What will be my next step?
Differentiate.
Nope. I have to find the limit.
find the
Yeah.
limit.
Yes. So the limit as x approaches infinity, right here,
Yeah.
of y, of natural log y equals limit as x approaches infinity from 2x plus 1 times natural log of 2x minus 3 over 2x plus 5. Notice now that this is a product. Whatever times whatever. So we have to see where they're going. Where is this going?
Infinity.
Yes. Now here, step by step. Where is this going? The inside.
Infinity.
Careful. Yes, it's infinity over infinity, but we determined that this piece
Is
approaches
1.
1. So this whole thing approaches 1. But now, how much is natural log 1? We all know natural log 1. I know for sure.
0.
Yes, remember the graph, right? It's right here. Good. So now we changed to what we had initially, 1 to infinity. It got changed into the product. But I know that the product is not hard. It only requires an algebraic manipulation, a tiny change. Do not ever try to change the natural log and bring it to the denominator. Never, ever. Because then you're bringing it with a negative power. So I have to work on this. So I'm not going to write here. I need to change this now into a fraction, into a ratio, so I can use L'Hopital's rule. So then I have limit as x approaches infinity. This stays where it is. And this has to go to the denominator, like this. Because I'm not allowed to change the function. The function has to be exactly what it's here, here. This hasn't changed, and 1 over this, I flip to get that. So I brought something from numerator to the denominator, but as 1 over, so I didn't change, so I don't change the function. And now, this is 0 over 0. This we know is 0, but now 1 over infinity is approaching 0. And the function is the same. But I needed this algebraic manipulation, 0 times infinity, algebraic manipulation. A minor change, but not changing the function, the outlook, the presentation of the function, but not the function itself. So that I can now continue with L'Hopital's rule. Okay, so now let's differentiate. Again, limit, ratio, 0 over 0 or infinity over infinity. All 3 conditions are fulfilled for L'Hopital's rule. L'Hopital's rule is applicable. I will change this into 2x plus 1 to -1, and I will differentiate it. Negative 2x plus 1 to -2 times the inner function prime. Now let's differentiate the top. Whoever chose this problem will be banned from choosing for the next 2 classes. Of course, I'm kidding. So we have to differentiate that. So it will be 1 over, so I'm going to flip it already, because it's 1 over this, which becomes 2x plus 5 over. And now I have to differentiate the inner function. 2x plus 5 squared. The top prime is 2 times the denominator minus the top times the denominator prime. Gee whiz. But that's good. Okay. Do we understand this step before we continue? Is that a yes? Is that a no? I haven't finished.
Yeah.
I have to simplify everything here. Okay, so number 1, I'm going to get rid of this gladly. 1 2x from the top, 2x plus 5, and 1, they're all factors. I'm not simplifying in a sum or difference. Okay, then I have limit as x approaches infinity. So I'm going to write in the denominator this times this, 2x minus 3 and 2x plus 5. I'm going to factor out a 2. And then I have 2x plus 5 minus 2x plus 3. Yay! And the denominator is -2 over 2x plus 1 squared. Okay, more algebra. So I have 8 times 2. So limit as x approaches infinity. 16 over 2x plus 3 to x plus 5 times negative 2x plus 1 squared over 2. Remember, it's multiplication. If you don't put parentheses, the whole thing collapses. Or you can put the minus in front, and you don't have to use parentheses. I will simplify the 2. I will put the -8 in front and limit as x approaches infinity. The numerator, I will expand it. Maybe not. I should just differentiate. I'm not going to expand it. 2x plus 1 squared over, it will be easier to expand this. So 4x squared plus 10, 10 and 6 plus 16x plus 15. Good. Yes, of course, infinity over infinity again. I'll differentiate the top, I'll differentiate the denominator again. This is nice, just polynomials. Finally, we cleaned it up completely. Limit as x approaches infinity. So 2x plus 1 times the inner function prime. The denominator is 8x plus 16. Okay. Limit as x approaches infinity. Again, of course, it's infinity over infinity. So this is 4 times 2 is 8x. 8x prime is 8. The denominator prime is 8. So the limit is -8. So when I differentiate the denominator, I get 8. 2 times 2 times 2 will be 8x plus 8. But when I differentiate that, I get 8. And this is 1, so this is the limit. Okay, 5 pages ago, I started. So I have to copy the beginning, which is limit as x approaches infinity from natural log y, and the answer is -8. At this point, I will swap natural log of the limit as x approaches infinity, and the limit was from this equals -8. And very nice. Can anyone tell us what is this limit? What is it? How much?
T to the power of -8.
That's it. Perfect. Excellent. Okay, I think we had enough of L'Hopital's rule. I would like us to continue and finish up graphing with 4.5. We're learning about more asymptotes here. That's the last thing about graphing, promise. We're going to learn a little bit more about asymptotes and graphs with holes in them. I would like to, with your permission, to we can look at any problem you want. This is it. That's the end of graphing application. But I like to start with a rational function that I will make up, and then we can choose.